Good morning. I would like to thank Professor Salim Shariar and wish him all the best and excellent health. Unfortunately, he cannot be there, so that's the reason I try to stay at the same time in Chicago with him and to send you again my presentation by again the way that you can see. So if I'm not there physically, my heart and my mind is with you. So the objective of my talk is the following: the introduction and the result for the phase log 3.8, 4.88 micron and continuous phase, and the summary and future. First of all, why? The application of high power multispectral tunable lasers are numerous. Between them, we can say high sensitivity chemical sensing, free space communication, adaptable infrared countermeasure, and many others. So high wavelength tunability, inter-subband transition, band gap engineering can exactly help, and the quantum cascade between 3 to 12 micron can be evoked at room temperature, compact, and suitable for the photonic integrated circuit development. That the objective of this talk is one of those. So one of the objectives is the feature here to have the high power multispectral hemispherical phase arrays beam steering system. So the key feature, exactly as you can see here, we can have here the platform, the QCL based arrays that we have to have the system that non-mechanical beam steering using optical phase arrays and multi-band operation in the infrared and integration of all components on a silicon-based platform. And if we take one unit here, the key challenge for the phase arrays emitters are the following: to have single wavelength output with fixed phase profile at output. And the targeting, we have three wavelength, the 3 to 4, 3 to 4 to 3.8 micron, and 4.5 to 4.9 micron, and 8 to 10.6 micron spectral range. And we would like to have up to 16 elements for each wavelength that to give higher than 10 watts continuous wave power output. So for that, we try to use the phase lock laser arrays, and the previous demonstration of phase lock the QCL arrays, it was in white the junction 3 arrays lasers at 4.6 micron with the 4 element with the 1.5 watts continuous wave power. And the problem here is the bisection has no selectivity over in and output of the phase modes, and the mode competition result in poor power scaling. That is published in 2014. And the evanescent wave coupled laser arrays with the at 8.4 micron with 5 element gave 5.5 watt peak power in phase mode, but the problem is required multi-step emissivity. Growth has very limited potential for continuous wave operation due to a small separation of the laser element, published 2015 from Dambote's group. And the tableau cavity coupled laser arrays at 4.6 micron with the 6 element exactly at 4 watt peak power and in and out of phase mode, but the problem is high coupling loss has limited potential for continuous wave operation, and due to large widths of the tableau cavity that is more than 100 milliwatt. That is published again in 2017. So we need the new phase arrays design is needed for continuous wave power scaling. So that is the thing that we try to come and to use the MMI based single mode high power and phase lock quantum cascade the laser arrays that I'm going to show you now. What we did, we tried to come with the multimode interferometer for power combining and splitting. That is the similar the things that they do in the short wavelength. So we tried to have 1 to 2 multimode interferometer. We designed to have a more than 98% power throughput for the quantum cascade on chip beam splitting and combining. And we try to design in order that to have the mode discrimination between in phase and out of phase mode, as they can see here. So the MMI were designed to support only in phase mode. exactly as you can see, and we use it for all of the different wavelengths. So here for the 4.8 micron band structure and characterization, we design again 4.8 micron with the active region based on strength balance superlatives in indium-phosphide gallium indium arsenide for the wavelength for 4.8 micron 40-stage laser core we used, and we got 23%, but the Volparac efficiency in pulse for the 20 micron the width using the double channel waveguide laser. You can see here, and after that we tried here to do the MMI combined high power phase lock quantum cascade laser arrays. As we can see here, that is the current as function of optical power for the Fabry Pro or the Fabry Pro 5, the 5 micron, and the 2 element and the 4 element and 8 element. So we demonstrated the power scaling of the QCL arrays, and the arrays are phase lock exactly as we can see here by a 3-array multimode interferometer MMI, as we can see 1, 2, and 3. Then the far field measurement indicated pure in-phase locking operation, and the device hold potential for high power continuous wave where the operation with up to 10 watt output power, and that we published in 2018 with my student at the Venjosu. So after that, we tried to come to design for the 18 element phase arrays the device, and that is exactly the difference part, the length of the DFB in order to have the single mode, and for the MMI optimization of the difference part DLW, exactly as we can see for the tier 3 difference wavelength 3.8 micron, 4.8 micron, and 8 micron, and we try to optimize that and to use it for the again the 3 wavelength. So here we try to do at the same time a kind of S-band waveguide optimization for throughput. The low loss S-band waveguide design is necessary for efficient beam splitting, and the systematic optimization for the 1 to 2 splitter with difference again element distance from each other is again calculated and optimized for the and determine the optimal geometry. So here the overall exactly the seed laser output power is evenly split in 2, 4, and 8 and 16 element, and the power among each element is about 4 to 5%. So by using that, we try to design now that we design again the structure that has, first we have the DFB grating part, and after that we try to have the MMI splitter and laser waveguide by using the plasma etching, again 1 to 2, 2 to 4, 4 to 8, and 8 to 14, and at the same time the device has and at the same time the amplifier, so exactly as we can see the device has the 3 different sections, DFB and MMI, and at the same time the splitter arrays and amplifier arrays, splitter arrays and amplifier arrays, and it has also a 4-degree angle facet termination when AR coated targeted facet reflectivity is less than 0.1%. As we can see, we use yttrium oxide, and that is the reflectivity of the yttrium oxide with the different thickness as function of the difference angle here, and we choose the 4-degree angle, and with the exactly with the 690 the nanometer yttrium oxide that give us the reflectivity less than 1%, and here we use that for the difference wavelength for the 4.8 micron. That is the design, and that is the result of the structure. And we have here now the world first 4.8 single mode 16 element high power phase lock, and we can see that we have up to again 30 watts, the 30 watts impulse operation with the 1% duty cycle, and that exactly is the single mode even up to 26.4 watt, and the central emission wavelength is 4.84, and the full width of half maximum is only 2 centimeter minus 1, 5 nanometer, and the far field of the device shows well-defined in-phase operation and is compared to 16 split Fraunhofer diffraction theory. Now we did at the same time for the 3.8 micron, shorter wavelength. And the same thing, the design of the structure is based on a strain balance, and we use the emission wavelength that calculated for to be 3.8 micron. 3-stage laser we use with the optical confinement of the 0.692 and the grating coupling coefficient 133 centimeter minus 1. That the result gave the 13% bulb plug efficiency for the width of the 20 micron length of the millimeter with the double channel waveguide lasers. And that with the 16 element, again, that's the world first 3.8 single mode, 16 element high power phase lock, as we can see on a 5 millimeter long device with both side AR coating, emit up to 20 watts, and the threshold current is about 4.8 kiloampere for this wavelength, and single mode emission have to obtain up to 20 watts, and the far field exhibit distinct peaks with separation of 4.5 degrees, which are characteristic of phase locking and indicate the uniform phase distribution across the array's output. Now we went to the 8 micron. For the 8 micron, again, we designed the structure for the 8 micron with the optical confinement of the 0.6. We use 45 stage, and the grating coupling is for 4.8. We got for that the bulb plug efficiency at 8 micron 20.4%. That is the highest bulb plug efficiency for the long wavelength, and with the width of the 7.6. And we use that again, as we can see, what first 8 micron single mode with the 16 element high power phase arrays, so that again the 16 element phase dot gave up to 51 watts with the 50 micron pitch and the AR coating on both facets, and the single mode operation has been obtained exactly as we can see with the high performance, and the far field exhibit distinct peaks with the separation of 10 degrees, which are characteristic of the phase locking and indicate a uniform phase distribution across the array output. So as we can see that is the Fabry Perot as a test, and the result, as we can see, for the 4.8 micron, but that is the phase lock, the 16 element phase lock, as we can see, 4.8 micron 30 watts, the 8 micron 51 watts, 3.8 20 watts peak power, and average power that we can see here. Now how to go to the continuous wave. For to do the continuous wave, in general, the QCL have a typical bulb plug efficiency between 5% and 20%. For achieving 10 watt output power, the base power can range between 40 watt to 190 according to have the 5% or 20% bulb plug efficiency. So the good thermal management at the same time is necessary for the demonstration of high power continuous wave phase lock. A strategy for the efficient heat management of QCL arrays include design of the highly efficient active region, epi layer down, buried ridge, selection of the wider array pitch, macro impeachment with the water cooling, and to have high absolutely the bulb plug efficiency. Because if we say that bulb plug efficiency with the output power, if you have the bulb plug efficiency with the 5% with the output power 5 watt, the waste heat is 95 watt. But if no, to come with the, instead of bulb plug efficiency 5% to put 20% with the 10 watts, but the output power, we have only 40 watts. So by using all of that, we tried one part to use the double channel and to do the episode down. We tried to do the semi-insulating indium phosphide rigorous. We did the buried ridge and epidome plus buried ridge. We have the epidome, buried ridge, waveguide are favorable for high thermal conductance. So for that, exactly we try to do at the same time the narrow waveguide, buried ridge processing, and double step rigorous technique, and the buried ridge structure provide a lower waveguide loss and higher heat dissipation capability, as we can see here, and that is the results. First, we did again a kind of the edge, we used the 8 the arrays and the for the optimization of the pitch, we did again the calculation, theoretical, that is the core temperature as function of the pitch feed. So we choose the 200, so laser core temperature increase as a function of pitch feeds, as we know, and we did the simulation, and we used it for the 8-element arrays with the 200 micron pitch. We designed for the continuous wave operation, and we use the double-step rigorous technique for the body dish processing, and the body dish structure provide a lower waveguide loss and higher heat dissipation. And we can see here that is the world first and world highest continuous wave lower. It was up to before a few years ago, or in our group, because we have no much better result, but I cannot speak because it's unfortunately it's ether. So as we can see here, exactly that is the result that we have, up to 4.2 watts with the threshold current. That is so. In conclusion, and at the same time, that is the measurement, that's the simulation. We see that continuous wave operation of the 8-element long wavelength infrared arrays. That's the world first. And in conclusion, I have to say that we try to demonstrate the world first MMI-based 16-channel OPA for the 3.8 micron with the 20 watts, 4.8 micron, 30 watts, 8.2, 51 watts in pulse operation, and the world first at the same time for the 8-channel continuous wave long wavelength phase lock, the continuous wave with the 4.2 watts from any that is the highest power for any long wavelength QCL at anywhere. And the future development of the optical phase arrays with up to 10 watts continuous wave output power for any wavelength band that is continuous, but unfortunately I cannot hear. So by that, I would like to thank you and to wish you excellent conference, and please take care of yourself, and all the best, and thank you. Bye-bye.